controllers you can connect to the switch.
So, but let's say every primary controller.
No. Like the switch physically has like a limit here.
Oh, well, it is.
I know Smash Bros. Has. I didn't even know. I thought it was like 4 seems to be the standard.
The Smash Bros. You can play 8.
I know Smash Bros. You can play with.
Wait, you can have 8 people at on one Switch?
Like Smash Bros.
No, really? You can connect all 8 controllers simultaneously?
Yeah.
You don't need 2 switches?
I didn't know that. You can do 8.
You can do 8?
Yeah.
Oh man. Alright, I gotta keep those control. I was gonna throw some out, but now I gotta keep them. Alright, sorry. That was exciting development. Alright, we're back. I think we're back. Yeah, we're back. Cool. So we were looking at this problem. We were defining, and it might have felt kind of weird. If it feels kind of weird, it is kind of weird. Like we're defining stuff without actually knowing what the values are, and we're trying to figure out how can we prove that some things are constant or 0, and that kind of work. So we chose a coordinate system. We said we're going to use polar coordinates for this like spring on this table, and the table's moving away. We looked at the moving reference frame and the fixed reference frame, like what the difference in position was. So here, I was using these like mixed coordinate systems where I have like a B1 and a radial, like R and theta coordinates, and that's okay. Like you can mix and match those unit vectors as long as you're not just like, they don't add directly together, but there are components of the two within each. All right, so then we drew our free body diagram, which felt pretty simple, almost too simple, but that's okay, because that's the only real force that we were looking at. And it's the only force acting on that object. The force of the spring is going to look kind of weird, like it's going to look weird because the table's moving, so there's both force of the spring like acting that way and then some kind of constraint to cause the motion. But I wanted to figure out, before we moved on to the next part where we were trying to figure out what is angular momentum, I want to know what is the sum of the moments around that moving frame, the O prime frame. What is the sum of the moments? That's what we're trying. So we have a force of the spring around this O prime point. How much torque does that spring create around O prime?
I don't think it creates any torque pointing towards the center.
It's a center-seeking kind of force, right? So it's not actually, there's no moment arm, even though the force can be really large, but it's not actually creating a torque. We can prove that, at least like if you want to, because I know this R of P O prime is its current radius times ER, like along that unit vector. What is the force of the spring? What's that unit vector? I know it's like a negative K, like, I know how big it is, right? R minus L0, if I say there's some unstretched length, and then R minus that unstretched is the, but what direction is it pointing in? Is it in the B1 direction, B2, ER, E theta? Where is this force pointing?
I think it's in the negative E.
Yeah, in that negative ER. So no matter how big R and KR are, ER cross ER is always 0. So sum of the moments has to be 0 around O prime. Cool. What are some of the moments around O? Is it also 0? What does the definition look like now? We only have that one force, so we only have to talk about the torque from that one force. What is our definition now? Before it was RPO prime crossed with FS. What's our new? What's our new? RPO. Yep. And we can use that same definition, right? Negative K R minus L0 along that ER. Is this still 0? Just want to check in and see. What do you think? Is it still 0?
It's like moving back as you go. It's like
Yep.
forward and back.
Yeah, so there's some function of time there, right? Yeah. So it can't be 0 all.
It's a spinning thing.
Okay.
On the
Yeah, because the
spring.
moment arm is changing.
On the table is being not pushed, the table is rolled.
Is this one 0? Is the moment around L?
Yes, O is the start of the table position. O prime is the center of the table.
Make it further away, right? Still stretching. Okay.
Well, yeah, because once I move, wouldn't there be a distance?
So far, 2 votes for, well, 3 votes for not 0. Might. So something's different about this one, right? Something's different. So if we're kind of looking at like the math, again, like mathing our way through the problem, we still have the same definition, like R cross R times that negative K R minus L0, that one's still going to be 0. But now I have this D0T, like a negative D0T times K R minus L0, with a B1 crossed with ER. And if we're and we can convert either B1 to ER and E theta or ER to B1 and B2, right? Because both of them are just describing directions. So this ER, I'm going to replace it now with, really it's like a cosine theta B1 plus a sine theta B2, kind of like that, just to get it back into like one set of unit vectors. What's B1 cross B2? B3, yeah. So like whoop, pointing up out of the page. So moment, at least for like stuff moving in a plane, your moment's always describing like how much torque you have out of the plane. why is this one not 0, but the first one, like, how come we can't just say this is a 0 moment system? Like, why does it change when we change what the origin is? Does that question make sense? Okay, yeah, why is that happening? Why can't we just say, like, there's no moment in this system?
I think because the table itself is moving, and there's an added distance of both the radius of the mass and the distance from the table to its original position.
Okay, yeah, so that motion is causing some kind of difference. Yeah. Is this always true that there's sometimes a 0 moment point, sometimes a non-zero moment point? Does that, like, can I always pick a system and always say, like, there's 0 moment around this point, but there's an applied moment around some other point sometimes? But, like, one of the main things that makes it, because, like, in a static system, the sum of the moments and the sum of the forces is just 0, just always 0, and it doesn't matter where you choose your reference point. But in a dynamic system, there are certain points where moments are 0, or so that because we have both position and force in that cross product, then we end up with, like, it depends on what you're saying is your reference frame based on, like, when you can say stuff is 0. Anyway, okay, cool. All right, so now, well, all right, so first, so we had this, so coming back here. What is the sum of the moments equal to? Like, sum of the forces is a change in linear momentum. What is the sum of the moments? A total moment on the system. If you apply a torque on something, what happens to it? It starts spinning. So what's the resistance to spinning? Spinning in the opposite direction. Like, so resistance to acceleration is mass. That's like, the bigger something is, the bigger the force you need to push it. So what is it for rotating? Yeah, like a moment of inertia, like how much inertia it has for rotation. Yeah, but yeah, like some kind of has some, trying to get it to move will create some kind of opposite torque on it. So if there's no moment around O prime, then the change in IO and like there's no change in our moment of inertia times theta dot. And like general way to write this is HO. Little h is our angular momentum. All right, so now we can go into the step of like, we have our free body diagram. We know around O prime, angular momentum is not changing. So the change in angular momentum is 0. So now let's say we have R of P O prime is R ER. V of P O prime is R dot ER plus R theta dot E theta what is our angular momentum? Do you know what the definition for angular momentum is?
The sum of all the masses.
Okay.
And its distance to the radius. So if you have like a point mass, its rotational inertia would be mr squared.
Mr squared? Okay, yeah, that's its rotational inertia. Yep. Like back up here. I think it's coming like that.
Yes.
Yeah. MVR, something like that. I omega, yeah. So like general kind of sum of the forces equals mass times acceleration. If we want sum of the moments, we're taking r cross the sum of the moments, which is also r cross ma. And really what I'm doing, so now this becomes sum of the moments is the change in r cross mv. That was like very quick derivation of, skipped a lot of steps, but derivation of like, what is angular momentum? This is h. And we're talking about like those relative positions and relative velocities in this case, right? I guess this is really like side note, right? Side note that's in the way. All right. So what do we think? What is the angular momentum of our little like mass moving around in this ellipse on the table?
So just put those in.
Yeah. 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 Just what is HO prime? So just plug those two equations into that cross product. Yeah. Yeah. Oh, so the same way like x cross y, ER cross a. Oh, okay.
That makes sense. Simple question. Because that's XY. I got R squared theta that easy.
In the easy direction. Yeah, E3, it could be B3, easy, or B3, just something like coming up out of the page. And we do have, the only extra part is just mass times that. So this definition for angular momentum, this is true for a point mass always in a polar coordinate system. Like it doesn't, this is always the angular momentum. This is I of a point mass, and then theta dot is like how fast it's moving. Yeah.
B1 and 2 kind of track a little bit more easily than like I and J, so I kind of get like how you know that these things are there. But with the PR and E data, like how do you know that like guess which direction it is to determine whether it was positive or negative?
Oh, so yeah, like when we have I, J, and then K coming out of the page, then we know like I, J, IJK, like if you're going clockwise, it's positive, and counterclockwise, negative. It's the same exact, nothing changes whenever I replace ER, E theta. So if it's ER cross E theta, positive K. If it's E theta cross ER, now it's a negative K. Yeah. Yeah, and cross products are weird because, like, if you flip, if I said that it was MV cross R, I would get a negative value. Yeah, it always seemed weird to me because the intuitive description of cross product is that it's the area created by those two vectors. Have you seen that or heard that? Yeah. Like A cross B is that area, but area is kind of weird because it does have a direction, whether you want to say it's a positive or a negative, like it's facing a different direction, whether you're describing the undersurface or the top surface. Yeah, it's the same area, but it's two different directions. That gets to be way more important if you're doing like defining surface contacts in like a fluid dynamics or FEA solution. Like, why is it not recognizing this contact? It's like, it's because you defined area in the wrong direction, so it doesn't actually see it until it crosses it, and then when you try to unload, now they're in contact with each other. All right, cool. Done. So the last step, we did all the hard work. So we already figured out what the sum of the moments are in each frame. When is angular momentum constant? Like which frame can we say that it's always the same value? So in our O prime frame, even though it's moving, like it's a moving frame, angular momentum around that O prime is always, whatever it started with, that's what it's going to be forever, at least based on our free body diagram. Like if it's real life, then maybe there's drag or friction or something. But what about in the O, if we're thinking about reference frame O, if that's our origin? What is that one telling us? What's happening to our angular momentum over time? It's changing, yep. By how much?
What was it, V0T?
V0T, so it's some kind of like every second there's more and more angular momentum around that O frame. Why is that important? What is that actually telling you? It's kind of a weird thing. Like if this was a design problem, you're like an engineer working on a design, someone tells you like, oh, it's a fixed, in this moving reference frame, angular momentum's constant, so we don't have to worry about torque. And you're like, yeah, but it's moving away, so there is torque back here where we started. What does that tell you about it? So think about like cable car, kind of like at some point if it starts moving around in a circle, it's never going to stop moving in a circle, right? So although there's no torque created on O prime, there's absolutely torque being created on where the support for that car is. And think about, this is like, they have these in construction sites and like shipyards and stuff. I'm like, all right, let's move this thing at a constant speed and start swinging around, like the wind gets it to start moving around. We are absolutely creating a big torque on O, even though torque on O prime equals 0. Kind of like that. So yeah, what your frame of reference is matters, even if you have inertial reference frames. Inertial means like constant speed kind of reference frame.
This scenario would it be like an imaginary torque because the cable's not like directly attached to the original point?
In that case, what would be happening is the floor is creating the torque somehow, right? At least if the table is like disconnected from, like it's not on a track. Yeah. Yeah, but the floor, somehow you're like preventing the table from like getting twisted around. Because really, if this thing's moving and the table is light, then the table would also be moving, depending on how heavy it is. Yeah. Anyway. Cool. And then I think, where are we at? Homework. What did we just, no, we're in module 4. What's going on? 9:14. All right, cool. I like this one. I think we're rolling off a table here. Here we go. All right, we've got a marble that's going to roll down a ramp, hit the table, roll forward across the table, and then fall off the table. The end result that we want is how far did it go? So once it leaves the table, it'll be like spinning and get to some distance. So what are we thinking for this problem? What's your first thought here?
Conservation of energy.
Conservation of energy. Where is energy conserved?
Everywhere.
Is it everywhere? Does it matter that the ramp is at an angle, that it's not like a smooth transition? Does the slope of the ramp affect its kinetic energy? No? Here's another question. Do speed bumps slow you down? Yeah. How do they slow you down?
You slow you down.
What?
You slow yourself down. Preparation.
Okay, so you think it's a psychological slowdown? Okay. I think there is a real slowdown because, I mean, if you hit a speed bump at 30 miles an hour, yeah, you break your suspension. Yeah.
You have to go pop a small rate of flying to get over this.
So you think it's the increase in potential energy? You're converting your forward kinetic energy into potential?
Well, I mean, it depends on how fast you're going.
Okay.
If you're going really fast, the collision will slow you down a little bit.
What about the collision slows you down? Yeah.
Because the tires can't move over the speed bump fast enough to not prevent there to be friction between the tires and the speed bump.
Oh, you think increase in friction? Change in friction?
So like, if the energy gets converted into like spring potential energy and suspension hits it.
Okay. But if it's spring potential energy, shouldn't you get it back?
It bounces you back up a whole.
Okay. Yeah.
This problem says it's not sloping. I don't know if it was sloping, but when it reaches the end of the ramp, and you're like, I don't know, it ground that has some impact on it, but since it's gonna be in contact with the ramp over time.
Yeah. You think then energy is conserved?
Yeah.
Energy conserved. What if W, like our width of the ramp, was 0? How fast is it moving forward as you drop it by height h?
It's not slowing down.
Okay.
So with the 0, it's not
It would fall forward. So if there's any slope, then we get all of our forward momentum back.
Well, I think the rolling is part of it.
The rolling, so maybe the rolling part. So what if it's like an 89.9 degree ramp, so it rolls down the ramp and then hits the table? Do we have anything that rolls? Oh, I got a car. Huh, for speed bumps. There we go. All right. So like we'll start top of, and you can't see it online, sorry, but so a car coming down, we'll start at the top of this thing, just so it's constant potential energy. Here, it's not 90 degrees, but it's close, right? Not a lot of speed versus some speed. More speed. Why did I get more speed as the angle kept changing?
Because the distance, like, of the slope is
Shouldn't that increase friction? Work done by friction? Longer time? Yeah.
Because when you make a really, really steep slope, the marbles no longer rolling up the ramp, it's colliding with the surface.
There's a collision. Yeah. And then impact with the ground. Okay. How was I change? What's the change in impact with the ground? Like, because now we're taught like impact and impulse. Those are sort of like the same thing. When somebody says like there was a large impact, that means that there was a big force in a small period of time, or something, right? Like big force, small time.
The shallower the angle, the smoother the transition.
Smoother transitions, yeah. Yeah, because we could get like a super smooth transition, right? That's like how, make sure I'm, going the right way. Not as great, but smoother transition, less impulse. And so that's how a speed bump works. It's like my NV was going forward. Now it has to go straight up. Or not straight up. If it's straight up, then you're going to come to a complete stop. So, but you're at an angle, right? And that's going to be based on like whatever component of MV was parallel to that new slope. So I lost it along that direction, and then as I come down off of it, the only like forward momentum was this like MV forward. So every like sharp transition, I lose whatever component is not parallel to that direction of the surface. Kind of weird, right? because every time there's an impact. And if it's like a perfectly elastic collision, then you would hit the speed bump and bounce over the speed bump. So yeah, you maintain all of your kinetic energy, but now you're like directed upwards. But that doesn't happen. We have dampers. Same thing here. When the marble hits the table, if it was a perfectly elastic collision with the table, it would hit and then start bouncing its way off the table. And that can happen, but sooner or later the bouncing goes to zero because it's not perfectly elastic. There's some coefficient of restitution, so we can say we lose that. So we can definitely use conservation of energy, but when there's an impact, we have to say there's some change in energy. Yeah.
So in regards to our problem, because the velocity of the marble goes from that to that, it loses some of its energy.
Yeah, so as we're coming, if we're kind of looking at like just this section, if I have like an MV of the slope, I can say that it's got some MVY, some MVX. There's going to be a large like F delta T that is equal to that MVY. So whatever momentum I had that's going down, the table is going to slam against it, and now the only thing left is that MVX as I'm coming off of it. Kind of like that. And also because it's rolling, like technically there's also like a increase in friction to change how fast it's rolling, but we don't have to worry about that as much. It'll do whatever it needs to. All right, so we do have conservation of energy. Where is it conserved? Because now we've got this spot where an impact happens. During a collision, in general, energy is not conserved. It's a very special case when it's conserved. That's usually it's just like atoms that conserve energy. And even there, you might, if you have like large collisions, something happens, like whatever, phonons are created or something. Electrons transfer. So usually, big collision, you can't say energy conserved, but we can use conservation angular, or sorry, we can use momentum, say like momentum is conserved or changed. So where are the points where energy is conserved?
I think from the top of the slope to the collision.
Okay.
Conserved in that portion.
Yeah.
And then after the collision, so when the ball hits the ground, energy is conserved in that portion.
So if I'm kind of labeling it as like position 1, we release the ball. Position 2, energy was conserved the whole way, or at least like kinetic plus potential conserved. And then 2 to 3, some kind of impact. We have to look at the change in momentum due to that impact. And then 3 to 4, energy conserved. And now 4 falls off the table. And I guess we could still say energy conserved all the way to 5. Something like that. Makes sense. the general formula, at least for dynamics, is just kinetic plus potential plus the work that it takes to get from 1 to 2 equals kinetic plus potential. So try to fill in these values, or you can cross, if there's 0, you can cross them out, but what are the kinetic and potential energies for this rolling marble as it's going down the ramp to get from 1 to 2? Sorry, yeah, I know. K-E-P-E. I know, there's always like a new variable. They're variables, they vary.
No, it's a release, like, is it initially rolls? Or is it
So it should just be ME21. Oh. Yeah, but then, so if we consider just height.
So in this case,
So it should be 1 MB squared.
These are the bottom of the slope, but not. At the bottom of the slope, it's got potential.
Yeah.
We said at the top, there's no potential. And then when it gets to the bottom, it's not.
Oh, it's just
also the bottom of the slope. So you're saying that.
So there should be some. So should be should be that's like the work done.
It's not all kinetic, you still have to.
Well, I think it's irrelevant. I think that's what that can play one's own.
Look at this. It's like.
yeah,
Yep. By the 4, like by the 4 by the distance.
I wonder if David is.
No one's watching.
Yeah, H, and like you, people, so you're just like this stuff is sour. Nobody can walk with that.
yeah, and you can have a negative potential energy, right?
Yeah.
Like if you say that
Oh.
assuming that after the table it goes to negative H2,
Yeah.
then that's okay. It's still a positive change, like at least it's still increase.
Yeah.
So your reference frame of H equals 0 can literally just like yeah, class is over. I know. Thanks. Okay, so thanks for joining. On Friday we'll have another guest lecture. Mohammed, Mr. Mundiwala, he'll be back and pick up where we left off, and then hopefully get into, I think plan will be look at the Francis Scott Key Bridge. That'll be like next step. I might even just delete this bar problem. But anyway, just because we're running out of time. We got things to do, right? All right, thanks a lot.